Welcome to Chemistry Online. Today we're going to talk about the molecular dipole in water. Recall that molecular compounds in which electron distribution is unsymmetrical around covalent bonds are referred to as polar compounds. The polarity originates due to differences in electronegativity between atoms in those covalent bonds. Electronegativity is a physical property that describes the ability of an atom to attract electrons towards itself. If you look at the periodic table, atoms in this corner up here will have the highest electronegativities. Down here we have the lowest. In general, as you go across in a period, electronegativity will increase, and as you go up in a group, electronegativity also increases. The most electronegative element is fluorine. If we look at the molecule HF, we have electronegativities of 2.1 for hydrogen and 4 for fluorine. This results in an electrostatic potential map that looks like this. Now remember that in an electrostatic potential map, the blue color represents the absence of electrons or a positive charge. Excess electrons are shown in red, and that's associated with a negative charge. That means that the HF covalent bond is polarized, and we show that with a dipole. Positive end down here, pointy end is the negative end where we have the electrons. Okay, let's look at water. Let's start by drawing the Lewis structure. Oxygen is group 6. We'll put 2 hydrogens around it, and we'll make bonds. Now, as I've drawn this Lewis structure, I've drawn it with the 2 hydrogens on the same side. That's because, according to the valence shell electron pair repulsion theory, we have 4 things around this oxygen, 2 unshared pairs and 2 hydrogens. That means the molecular geometry of this will be bent. The electron pair geometry is tetrahedral, but the molecular geometry, that is, between the atoms here, is going to be bent. So this is what water looks like. Now, the electronegativities here are 3.5 for hydrogen, 2.1 for oxygen. That means that each of these bonds has a separate dipole, but the molecule as a whole has a molecular dipole. That is, this end of the molecule is going to be positive, and this end will be negative. We can show this in an electrostatic potential map that looks like this. And again, this is our positive end, and this is our negative end. Now, this polar nature of water is what's going to allow water to dissolve things like ionic compounds. We're going to form solutions. Remember, these are homogeneous mixtures. When something like sodium chloride dissolves in water, it does it in a very specific manner, such that the anion, the chloride, is surrounded by waters, but the waters are oriented so that the positive end of the dipole comes in contact with the chloride anion. This disperses the charge and stabilizes it. For the cation, we have just the opposite. The negative end of the water dipole associates with the sodium cation. Once again, it disperses the charge and stabilizes it in solution. This feature of water is a thing that allows water to dissolve things like ionic compounds, and we'll see later will actually allow it to break covalent bonds in ionizable molecular compounds.